Let us now understand the structural and magnetic analysis of these one-dimensional nanostructures. So basically, we are talking about the nanowires here. So this shows the XRD image or the XRD spectra of different nanowires deposited in the anodic alumina template. Corresponding to the structural parameters, in the XRD, we get different reflection planes. So it can be depending upon if we have multiple reflection planes. So we have a polycrystalline material. If we have a broad peak, that corresponds to the amorphous phase, and if we have only a single reflection plane, so that corresponds to, or multiple reflection planes but corresponding to multiple like 100, 200, 300, 400. So that corresponds, so that belongs to a family of 100 plane. So that is the single crystalline material. So XRD data helps us to understand what is the structure of the material which we are depositing. Say, suppose if I'm depositing nickel, or if I'm depositing cobalt, if I'm depositing any other material, whether it belongs to a simple cubic structure, it belongs to a body-centered cubic structure, it belongs to a face-centered cubic structure, woolsite structure. For the case of ZNO materials, we have woolsite structure, or any other type of crystalline properties, structural parameters are determined using the X-ray diffraction technique. We can analyze the X-ray diffraction and determine different parameters such as crystallite size, the lattice parameters, etc. For the case of nanowires, we basically determine these two parameters, but for different materials, we can also determine what is the strain present in the system, what are the space group to which it belongs. So we can determine various different parameters using the X-ray diffraction spectra. The magnetic properties, basically DC magnetic properties, are determined using the vibrating sample magnetometer technique, which is VSM or SQUID. So this shows the magnetic properties or the hysteresis loop of 30 nanometer long nickel nanowires, which are deposited in the anodic alumina template. So we have done two different orientation analysis. One is the parallel and another one is the perpendicular. So what does the parallel and perpendicular means? So suppose if you have a nanowire, so this is my nanowire. Basically, when the deposition takes place, the magnetic movements will try to orient themselves in a specific direction. So usually, the magnetic movements will try to orient along the long axis of the nanowire or along the easy axis. So this is known as the easy axis. And if I apply the magnetic field along this direction, it will be easier for the magnetic movements to align quickly along the field direction. So that is the easy axis. That's why it is known as the easy axis. But suppose if I apply the magnetic field along the perpendicular direction, then these magnetic movements will have to do the work to change its orientation from the easy axis to the perpendicular axis. So they have to change their orientation from the easy axis to perpendicular axis. So this change in behavior can be understood from the hysteresis loop. So you can see here that the easy axis will be more squared as compared to the perpendicular axis. So the parallel and perpendicular axis magnetic measurements helps us to understand that in which direction my magnetic movements are oriented. And it also helps to determine various different parameters like what is the remanence, what is the coercivity, what is the squareness present in the magnetic movement. So we can determine different properties by analyzing the hysteresis loop of the magnetic materials. So the next slide talks about the microwave measurement setup. So till now we have discussed about the structural parameters, morphological parameters, the basics we have deposited the magnetic materials, and then we have analyzed whether that specific material which we have deposited is giving the characteristics of that specific material or not. Now, this is the microwave measurements which we do are basically works in a different category to analyze the intrinsic material or intrinsic magnetic properties of the material, and also it will help us to fabricate different devices. So this shows the microwave measurement setup. So you can see here that for doing the microwave measurement setups, we basically use a vector network analyzer, and it has a two port, port 1 and port 2, which transmits the RF signal, and it receives the another port will receives the RF signal. Then we have a microstrip, so which the zoom view of this is shown. So this is a microstrip line, and we can fabricate this microstrip line on the material which we are using under investigation, or we can also we can use another microstrip line, and we can put our material over the microstrip line also. So this is the on-chip device measurements of a band stop or notch filter. So what we basically use here, we have not applied any external magnetic field. So we have not used any external magnetic field. So another property of these one-dimensional magnetic materials is that, as I said in the previous slide, that these magnetic materials orient their magnetic movements along the z-axis. So their magnetic movements work as a permanent magnet. So if I take a single wire whose all magnetic movements are aligned in a single direction, or along the z-axis, then that single nanowire will work as a permanent magnet. So even if I do not apply any external magnetic field, that specific permanent magnet is precessing around its equilibrium position. So if I apply an external RF magnetic field which is perpendicular to the precession with which this magnetic field is precessing. So DC magnetic field I have not applied. So the RF precession frequency and the precession frequency of my magnetization, wherever it matches, there will be a resonance, and that specific resonance is known as the Larmor frequency. There the resonance will occur, and that specific frequency where the resonance will occur is known as the Larmor frequency. We can tune the Larmor frequency or the operational frequency of these materials by applying the external magnetic field as well. So this image shows that if you use the Helmholtz coil and you vary the magnetic field, what will happen? Your Larmor frequency or the operational frequency will go towards the higher resonance frequency regions. So this is one of the advantage, and it can overcome various use of bulky magnets in devices, in microwave devices, such as wherever we are using the ferrites. So ferrites basically require permanent magnets or to tune their magnetic properties. But if we use these nanowires, we do not even require the magnetic field. Even without the magnetic field, they show the resonance behavior. They show the external absorption at a specific frequency. So miniaturization of microwave devices is possible using these one-dimensional nanostructures. Now, what are the different types of microwave devices which we can fabricate on these AO templates, in these ferromagnetic field AO templates? So there are various categories of these materials. So if I deposit a simple microstrip line on these AO templates, then this serves as a bandstop filter, as well as it can serve as a phase shifter. If I determine the magnitude of the resonance of the transmission line, that will serve as the bandstop filter. And if I know the phase of that specific material, that will be termed as the phase shifter. That can be used for the phase shifter. The isolator is another category. So isolator is a type of device. If you transmit the signal from port 1 to port 2, so what it basically do, it transmit that specific signal. But when it transmits from port 2 to port 1, the same signal, the properties will change. The behavior will not remain the same. So that it creates an isolation between the sending of the information. So you can send the information from one port to another port, but when you want to transmit the information from port 2 to port 1, it won't be possible. So isolator can be fabricated on these ferromagnetic nanostructure templates. Then we can also design bandpass filters also. So if I want to understand what are these things, so stop band filter is a filter which will allow all the frequencies in a specific range, but it will stop a specific band of frequencies from passing through the signal. So that is the stop band filter. The band pass filter works in opposite way. So it will not allow all the frequencies to pass or transmit through the signal, but it will allow only a band of frequencies from F1 to F2 to transmit from the microstrip line. The phase shifter, on the other hand, you can see phase shifter means that it shows a phase variation when we transmit the signal. So say when I transmit the signal, I am at the red line, but when I received, it will be at a phase difference of pi by 4. So there will be a phase difference between that. So these structures can be used as the phase shifter as well. Now, when we do the measurements of these microwave devices on the ferromagnetic nanowire substrates, so this shows the iron, cobalt, boron nanowire based filter. So what we basically have, you can see here, when I take the measurements for different magnetic fields, we can have a tuning of the operational frequency. So the graph 1 shows the FMR spectra of the cobalt, iron, boron nanowires band stop filter, and the right hand side graph shows the data points for the resonance frequency which we obtained, and the red line shows these are the red line is a theoretical plot, and the dot is the experimental data points corresponding to the resonance frequency. So we can tune the operational frequency by applying the external magnetic field in these structures. The same thing that is for the band stop filter, the same thing can be applied if we measure the phase of that specific material. So this shows again the phase shifter device, and if you see here, so the phase shifter, if you will see, operates in the low frequency region and high frequency region. So basically, we do not operate in the resonance frequency region for a phase shifter. We look at the low frequency region and the high frequency region. So you will see that there is a phase variation from the low frequency region to high frequency region, and this red line shows and red line and blue line shows the same thing, the low frequency region and the high frequency region. And so these devices can be used as the band stop filter as well as for the phase shifter, isolator, and other devices. Okay. So the same materials can be used again as a band pass filter as well as for the phase shifters also. Here you can see the band stop filter response of different nanowires. So their operational frequency will change depending upon the material which we are depositing. So if you see the nickel material, their operational frequency is in the range of 10 gigahertz to 20 gigahertz for a field of 0 to 5 kilo Orested. Whereas if you see for the cobalt nanowires, their resonance frequency is much higher because the cobalt has a more saturation magnetization as compared to the nickel. So their resonance frequency will lie in a higher frequency range. So their frequency will go from say 28 gigahertz to 32 gigahertz for a frequency range of this. So these graphs show that which specific material gives me better line width, which graph will give me more operational frequency, and which can be, so depending upon the material also we can opt for different materials to have different kind of devices. So suppose if I want to have a material which has a higher operational frequency range, I will go for the cobalt. And if I want a material which has a narrow line width, which is basically used for spintronics, so I will go for cobalt iron boron nanowires in that case. So this shows the different resonance frequency, the absorption, the line width, as well as the phase shifter response of different nanowire materials. So we can see that the resonance frequency increases linearly with applied magnetic field, giving a maximum frequency tunability of 110 for nickel and nickel iron alloy nanowires. And by proper choice of material, the frequency bands can also be tuned. Further, the line width decreases with the increase of a magnetic field. A maximum shift of 75 degree per centimeter at 4 kiloarsted was observed for nickel nanowires based devices. So the appropriate choice of materials can help us to choose the kind of device we want to design. Okay, so here we have investigated not the microwave devices, but we have investigated the angular variation or the magnetization reversal mechanisms in these nanowires. So if you can see here in this picture, we have these nanowires and they have different orientation. So they have the orbital angular momentum and the azimuthal angular momentum corresponding to the magnetization and the applied magnetic field. So if I change the angular variation in which I am applying the external magnetic field. So if you see, these are the nanowires. This is the external magnetic field in this direction. So the angle theta is 0 degree here. So the theta uh, is 0 degree corresponding to when the external magnetic field and the easy axis of the magnetization are parallel to each other. Now if I change the orientation of this microstrip line from say 0, or I tilt this sample position, then my angle will change. So depending upon the change in the angle, so from the parallel direction to the perpendicular direction, what I see that the nanowires and nanotubes show different behavior. They show the opposite behavior, and corresponding to this reversal mechanism, change in the behavior from 0 degree to 90 degree, or from 0 degree to 90 degree, we can interpret different parameters corresponding to what is the magnetic modes which are present in these one-dimensional nanostructures. So the magnetization reversal processes can be observed by analyzing the angular variation of resonance frequencies for these nanowires and nanotubes. And nanowires, what we observe that the magnetization